Hey everyone, this is Connor Mead with the Calculation Center. I'm here with another video in our calculus series going over integration by parts. Now, integration by parts is often a little messier than integration by substitution. However, once you know the formula and have gone through a couple of questions, it becomes very intuitive on how to do it. If you haven't seen this before, I'll mention the rule. It says that if we have the integral of f of x times g prime of x, so g prime is the derivative of some function g, then this is actually equal to, it's the indefinite integral of this quantity, is equal to f of x times g of x minus the integral of f prime of x g of x. So it comes out as the product of f of x, which is this function, and g of x, where g is some antiderivative of g prime, minus, and this is the same as the first integral, except now instead of differentiating g, we're differentiating f, okay? So this might seem like a strange rule, and it might be hard to see why it's useful, because we have an integral we want to solve on this side, and we have an integral that we may or may not be able to solve on this side. But the important thing is we're going to be careful in choosing f and g so that this integral over here is actually quite easy to solve, or at least something we can work with. Okay, and just as a side note, when we're talking about definite integrals, that is to say our lower bound being a, our upper bound being b for some real numbers a and b, we just have to substitute in this on the right hand side via saying that this quantity here is interpreted as it always is in integration, that this is actually equal to f of b g of b minus f of a g of a. So we're substituting in the upper bound and the lower bound here, basically, like in normal integration. And the upper bounds are also carried over here onto this side, okay? So let's go over some examples and we can see how we kind of make it work. So here's our first example, the integral from 0 to pi of x sine x dx, okay? So how I would always recommend going about this is writing down f of, so this function here, if we're going to use integration by parts, it has to be made up of an f of x and a g prime of x. So we have to think of which of these, there's basically two functions here, x and sine of x, and we have to decide which one's which. Well, recall that we're going to differentiate f, right? The f of x is going to get transformed into an f prime of x in the integral on the other side, and g prime of x is going to become g of x. So if we chose g prime of x to be x, then g of x would be x squared over 2 plus c. If we choose g prime of x to be sine of x, then g of x will be cosine of x. Similarly, if we choose f of x to be x, we'll end up with an f prime of x under the integral, and that'll just be 1. So that'll actually be very easy to work with. So therefore, we're going to choose f of x to be equal to x, okay? And g prime of x to be equal to sine of x. Now at this point, I'd also recommend computing f prime of x, which in this case is just 1, and g of x. So what do you have to differentiate to get sine of x? Well, it would have to be minus cosine of x. Okay? So this whole thing is equal to, so what's our first term? It's f of x times g of x. So it's equal to x, so I suppose minus x cos x, evaluated between 0 and pi, minus the integral of f prime g. So this is minus 1 times minus cos x, so that'll become plus cos x between 0 and pi. Okay? So this here evaluates to minus pi times the cosine of pi, which is 0. Is that right? No, it's minus 1, right? Minus 0. Well, plus 0, I guess. So that term vanishes. Plus pi times, well, let's be careful here. Well, this is the integral of cosine of x, so we need to think about what do you need to integrate to get, or what you need to differentiate to get cosine of x, and that is, of course, just sine x. So this becomes sine x. Evaluated between these points, we'll just get sine of pi, so that'll vanish and be 0. Okay, so this, and so therefore cos of pi is equal to minus 1. Let's just verify this to be careful. So cosine of x looks like this. So here we're at 1 when we're at 0. This is pi over 2. So this is pi. So therefore cos of pi is indeed equal to minus 1. So the answer is indeed pi. Okay, so that's the first one. Now I'd also recommend as an exercise to you guys, see what happens if you try and let f of x to be equal to sine x and g prime of x to be equal to x. You're going to see that this actually isn't going to work out very well for you, and you'll end up with a problem more difficult to solve. So it is important that you basically, generally speaking, it's nice to choose monomials as a thing you're going to differentiate, because that will end up decreasing the difficulty of the problem, because you'll be ending up with a smaller monomial. Okay? Now this question is kind of an unusual example, I would say, because this function doesn't look like the product of any functions, but we kind of need to figure out what the integral of ln of x dx is, so I thought I'd put it in here, because you do use the rule of integration by parts here. So what can we do here? Well, we can let f of x equal to ln of x, and that would mean g prime of x would have to be equal to, well, what is ln of x multiplied by here? Well, it's actually just 1, right? And now we can apply integration by substitution, integration by parts, I should say, on this step. So f prime of x, the derivative of ln x, we know it's 1 over x, and g prime of x is equal to 1, so that means g of x is equal to x. And now we can do integration by substitution, or by parts, I mean. So you end up with an x ln x plus, or rather minus, the integral of f prime times g, and f prime times g is x times 1 over x dx. So this is equal to x ln x minus the integral of 1 dx. So this is equal to x ln x minus c. However, minus c is just adding on some constant, so we can say plus c and it doesn't matter here, because c could be negative, for example. So this is actually the antiderivative of ln of x. It's x ln of x plus c. Okay? That one was just, because we really need to get that done, because we don't talk about it in the integration by the kind of standard integration rules. You really have to derive out what the integral of ln of x is. Okay? Lastly, we're going to talk about the integral of x squared e to the x. So we're going to take f prime of x. Like I say, it's good to take monomials here, because it will end up decreasing the power up here. So this 2 is going to decrease when we differentiate it. And that would mean, sorry, that should be an f, sorry, that's a mistake by me. F of x is equal to x squared, g of x prime is equal to e to the x. And notice that it's nice that we choose g prime e to the x, because then g of x is also equal to e to the x. F prime of x is equal to 2x, and let's go. F times g is equal to x squared e to the x, and we're subtracting off f prime times g, so that's minus 2 times the integral of x e to the x dx. Now the problem is this doesn't actually look any better, because we still don't know how to integrate this. However, compare this to our initial problem of x squared e to the x, and notice that we've decreased the power up here by 1. And why is that good? Because now we can just apply integration by parts again. So this is x squared e to the x minus 2. And now we're going to apply integration by parts to this entire thing. I better give myself some space, actually. I'm going to reuse notation here, but hopefully it's not confusing. So f is going to be equal to x. G prime is going to be equal to e to the x again. So therefore f prime is equal to 1, and g is equal to e to the x. So this becomes minus 2 times, so we need to get fg, so that's x e to the x, minus the integral of f prime g, which is just e to the x dx. Okay? So, and this integral is easy to work out because we've decreased the power up here again. This was an x to the 1, now it's an x to the 0. So now our answer overall is equal to x squared e to the x minus 2x e to the x plus 2 e to the x plus c, with a plus c coming from our final evaluation of this integral here. Okay, so notice that integration by parts actually often quite nicely stacks on itself and can be used to repeatedly decrease monomials multiplied by functions that are nice after differentiation. Okay, this has been Connor Mead with the Calculation Center, and I'll see you guys next time.